Welcome to today's lesson, which is lesson number 20 of the course on industrial automation and control. Today we are going to look at some new programming elements, namely timers, counters, etc., which are required for RLL programming. We are going to understand their meanings and see their use in real, simple but real typical industrial programs. So before we get on, we take a look at the instructional objective, which is so that a student will be familiarized, or he will be able to describe various types of timers used in relay ladder logic. He will be able to describe a counter. He will be able to construct RLL programs for simple problems involving these timers and counters, and he will also be able to be familiar with some program control, data transfer and arithmetic instructions which are required in, just like in any program you require if then else statements, which are program control statements, add statements, you need statements for moving data from one location to the other. So here also you need such constructs. So for writing complete programs they are sometimes necessary, so we will get familiarized with some of them. Of course, we must remember in this context that there are relay ladder logic programs are often somewhat non-standard. So it's not that we are following a particular manufacturer's constructs, but it is very likely that most of these constructs will be found in each PLC manufacturer's programming repertoire. So it's good to understand them in an abstract form, and then if you are going to use a particular PLC, then look up the particular manual for such constructs. So before we use timers and counters, we want to motivate them. So we take a second look at our previous example of the die press. So here is a die press where basically there is the piston moves the die up or down depending on whether the up solenoid or the down solenoid is activated. This directs hydraulic power upward or downward to the piston, so the die moves up or down. And there are two sensors, namely the upper limit switch and the lower limit switch, which sends the positions of the end positions of the die. So we take a look at the earlier solution which we proposed before in an earlier lesson. So here what we did is here we proposed an RLL program which used only the normally on and the NO, and there is a normally open and the normally closed contacts, the real input contacts as well as some auxiliary contacts and some output coils. Now what happens here is that let's look at this, that initially suppose the down solenoid is on. So the down solenoid is on means this is on. So this is on. When this is on, obviously because you have an NC contact here, so therefore up solenoid is off. So the die platform is coming down. When it comes down, it eventually makes the down limit switch, and the down lamp will go on. So this goes to 1. Immediately what will happen is that this, right, previously the path that was being followed for connection was this, so this down solenoid will become off. So now at this position the down solenoid is off and the up solenoid is off, so the piston is slowing down. There is no force forcing it down, so it's slowing down. Now what happens in this program is that the moment the down lamp is, so in this position the down lamp is on and the down solenoid has become off. So now what happens here is that the down lamp is on, so it becomes on, while the down solenoid is now also on. So this is also on because the down solenoid is off. So and this is a normally closed contact. Because this is a normally closed contact, so therefore when the down solenoid is off, this is on. So therefore immediately the up solenoid becomes on. So you see that normally for a die press, the die has to come down on the, suppose it's a sheet metal on which you are trying to press into a particular form, then you don't want that the moment it comes below immediately it goes up. You want it to probably wait a little while and then go up for the next stamp. So now it is it may be very common that a time delay between up solenoid and down solenoid is needed. That is, after the down lamp is on and by the time the up solenoid again becomes energized, we want a delay. So what I wanted to say here is that such delays are very often needed in industrial operations, and today we will see how to create these delays. Okay. So we go on. So now, so as we shall see, we will actually see the solution a little later, but first let us look at the timers which actually creates these delays. Now here I want to mention that these timers, the timers are sometimes we are all familiar with timers. Possibly our first interaction with introduction to timers was in the digital electronics course. Now those timers are actually hardware timers. You may actually use hardware timers also in a PLC, in which case you may have a separate timer card. But in this case we are talking of the program, so it's actually a piece of code which creates a delay in asserting some output, right? So the purpose of the timer is to create the delay. How much delay that can be programmed, number one. And number two is that the timer actually, it's the basic idea of a timer is that there are two registers. One is called the preset register and the other is called the timing register. So the preset register is actually set whenever you create a timer in the program, you actually set the preset register gets loaded by a particular value and it stays fixed. While the timing register, during the time that the timer is working, is active, the timing register keeps getting incremented using pulses from an internal clock of the PLC. So it does not require any external clock. Sometimes you may also, for example, as we shall see that counters are actually work on the external clock. So because we want a particular timing, so generally it is fed from the internal clock. So as the timing pulses from the clock are coming, so the timing register keeps increasing, and when its value exceeds that, every time there is a comparison between the timing register and the preset register. So after some time what will happen is that the timing register value will exceed the preset register value, at which time the timer will stop timing further, that is the timing register will stop incrementing and the output will be asserted. So the output will be asserted when TR equal to PR, right? Now this thing happens when the timer is active. So when is this timer active? That can be again controlled by using two kinds of logic. So first is called the enable or reset logic. So whenever this logic becomes 0, the timer is not enabled, it it's inactive and the output coil is reset to 1. So this output coil reset to 1. When that is why it's called reset logic, reset to 0, I'm sorry, reset to 0. Similarly, now when it is enabled, so at that time it is enabled to time, but whether it will actually time or not, that can be again controlled by this run logic. So when this run logic will be enabled, at that time only the timing pulses come from the internal clock to the timing register, at other times it is inhibited. Okay. So I would also like to assert mention that while in this case we have mentioned we have actually put it by a single contact, we could easily implement a complex logic based on which we want to enable or we want to assert the run logic. For that we can put extra rungs and which will actually program the logic, and then finally when the logic is satisfied or not, that will be simplified by that will be symbolized by an output coil. That output coil contact we can put it here. So it's not necessary that you will have to always make it a very simple logic, you can make it as complex a logic as you want. So having done that, so this is a basic timer. Now timers create delay, so we can have various types of delays, and all of them can be realized by this basic timer module. So to recapitulate, we have enable reset logic where the timing register is held at 0 when it is de-energized or 0, and the timer is enabled when 1. So at that time the timer is ready to receive the clock pulses and increment its values. Similarly, we have run logic where timing register increments with the internal clock when the enabled reset logic is 1, that is the timer is enabled, and the run logic is also 1, just what I said. So now we take a look at the different kinds of timers. First is the on delay timer. So here we are saying that if an input timer creates a delay between an input and an output. So here we say that if the input signal goes on, then the output signal will go on after a little delay. That delay, that's why it's called an on delay. So while the input signal becomes on, the output signal becomes on after a delay, but if the input signal goes off, then the output signal goes off immediately. So there is no delay in getting off. There is a delay in getting on. That is why it's called an on delay timer. Similarly, note here that here again it becomes on. So here again it becomes on. Now the timer, if this on would have persisted, then the timer would have been on somewhere over here. The timer would have been on. Because of this delay, but unfortunately the input became off. Unfortunately or fortunately, the input became off even before this delay interval could expire. So the timer also became off, and that delay value got erased. So the timer never went on. Similarly, now we will see that we can easily realize this on delay timer using our old timer. So now here is a circuit, here is a RLL logic circuit or a number of rungs which takes the basic timer unit. This is the basic timer unit that we have seen, takes it and couples it with another rung and makes an on delay timer. How? So suppose we asserted this input and we want that, so immediately when you asserted this output goes high, So immediately when we asserted this, this output goes high. But we want that the other output, that is OP002, actually go high after a short delay. So what happens is that this, whenever this OP001 goes on, so you see that the run logic is enabled and the enable reset logic is also enabled, which means that the timer is timing now. So, and when the delay, so the timing register is getting incremented with the internal clock pulses, and when it will cross the preset register, at that time the OP002 signal will go up. So you have, this is wrong. So you have created a delay. What is the on delay now? So the on delay is this much. So this is the on delay. On the other hand, see, the moment this becomes off, so the moment this becomes off, immediately these two become off, and immediately the OP002 also becomes off. So there is no delay in getting off, while there is some delay in getting on. That's why it's called an on delay timer. So let us see the other kinds of timers. Now, before doing that, let us now, so we want an on delay, let us use this on delay timer now in our die press example to see whether we can introduce a delay between the, that is after the down lamp goes on, we want that the up solenoid will go on after an on delay, right? So we do that. So here is our, our earlier, the first two rungs are very similar to our earlier solution, except for this one. I'm sorry. So except for this one, right? So now what is happening is that suppose the down solenoid is, the down solenoid was on. So actually the connection was coming like this. At this point the down lamp suddenly became on. The down lamp became on because the die hit the limit switch, down limit switch. So the moment the down lamp becomes on, so this will off, and the down solenoid now goes down. Now now look at this. So initially the OP002 is off, so therefore this is off, and MCS, this is the master switch, this also becomes off. So initially supply was coming up to this. Now the down lamp has become on. So immediately OP001 becomes on. When OP001 becomes on, the timer is enabled and it's timing. So after a delay, this OP002 goes on, becomes on. When this becomes on, now there is a direct path to this, and up solenoid becomes on. And when up solenoid becomes on, so then the usual operation starts. So what we have demonstrated is that we have put a timer rung, and now there is a time delay which can be set by the value of the preset register that we set here between the down lamp coming on and the up solenoid coming on. So that is what we have achieved. So now we look at the other different types of timers, for example off delay. So the off delay timer is exactly like the on delay timer, except for the fact that now the delay is getting off. So, the moment the input becomes on, the output also becomes on, no delay. But when the input becomes off, the output becomes off after a certain delay. So, this is the delay. This is the delay. Okay. And the same phenomenon is actually observed, that if this becomes on again for a short pulse, so this also becomes on. Then when it becomes off, here, this delay starts here, but before the delay, and then after this delay, this becomes off. But in this case, before this this delay can expire, there is another on, so it will again become on. So this cannot fall because the delay has not expired, so it continues. And then at the end of this, again after delay, it becomes off. So basically the same, but just a very similar operation with the on delay, but only applicable in this case when the input goes from on to off. So how do we realize this one? So that's simple to realize. So you see that now we are having off delay. So again, this is the input, goes on. So immediately OP001 goes on. When OP001 goes on, you see IN001, this is already off in the reset position, so OP003 immediately goes on. This is my final output. So there is no delay in getting on. Now suppose, and when OP003 goes off, we can use this one, so it latches. Now imagine that IN001 goes off. So when it goes off, this OP001, when this goes off, now these are NC contacts. So when all the time when this was on, this OP002 was held to 0. Now when it will be 0, then immediately the timer will start timing, and after some time this will become go high, become on. When this becomes on, immediately when this becomes on, this becomes off, and OP003 falls down. So there is a delay in getting OP003 off. So this is a very simple realization of the off delay timer, again using the basic timer construct that we have seen. Similarly, we could have various kinds of timers. For example, we could have a fixed pulse width timer, where every time the input becomes on, there is a, irrespective of the delay, you will get a fixed pulse from the output. So here this is just like an off delay timer. Yes, no, not an off delay timer. This is that every time when the input goes high, the output immediately goes high, and irrespective of the input, it stays for only for a fixed time and then comes down. So here also, when this goes high, and even if this comes down much earlier, this keeps. So here it does not come down, but still this comes down, and here it comes down, but still this does not come down. So every time you get the same pulse width. So every time this edge comes, this ongoing edge at the input, you get a fixed pulse at the output. This is the fixed pulse width timer, and it will be an interesting exercise for you to see how this can be realized using our basic timer construct. So that's a point to ponder for you. Next is that we again can classify timers into two ways. One is called retentive timer, another is called non-retentive timer. So for a non-retentive timer, what happens is that see the input here goes up, so the timing register starts increasing, suppose it's an on delay timer. After some time what happens is that the input comes down. Now the question is at this point, so it has timed up to certain amount, it has not reached its preset value. So now the question is that what will happen to the, but the input has come down. So what would happen to the timing register value at this point? So in non-retentive timers, the timing register value is reset to 0. So every time you get another timing signal, it again times, and in this time, because the input stays 1 for a much longer time, so the preset value is reached, and when it is reached, the timer output is asserted. See here the timer output is not asserted because the timing register did not exceed the preset register value. So this is called a non-retentive timer. Contrasted to this, there is a retentive timer, which now note the difference here. Here also, when the input goes 1 and then after some time it comes down, so the timing register value, so the timing register value came up to this. It actually did not cross the preset register, so the output is maintained to 0. Now when this input falls down, at this time also the timing register value is not lost, but it is held. So as long as the input is 0, it is held. For the next pulse, it counts from the previous value. So that's why it retains its timing register value. That's why it's called a retentive timer. Finally, as this increases, at some point, maybe for the next pulse, it reaches the preset register value, and at that point, the timer goes high. Okay, so this is the semantics or meaning of the way the retentive timer works. So so these are roughly the various kinds of timers available, and now we take a look at what is known as the counter. Okay, so now the counter is nothing but, frankly speaking, the counter is nothing but a timer with an external pulse. So now in the counter also there are two registers. One is called a preset register and another is a count register. But only thing is that in the timer, the timing register is incremented by an internal clock at regular intervals of time. So the timer is nothing but a counter which counts the timing pulses from an internal clock. While for the count register, for the counter, this count, you are trying to count something, maybe the number of parts produced, or the number of parts arrived on a conveyor, or something like that. So in which case, with every event taking place, you have to generate some kind of a pulse using again contacts and sensors. Now those external pulses in this case will actually augment the count register. So that counter is, in place of the internal clock pulses which were coming at the timer, here we have external pulses which are triggered by the events that we want to count. So again you have enable reset logic, same thing. In this case we have what is known as a count logic rather than a timer run logic. So the count register is incremented by 1 every time count logic goes high. So every time this goes high from 0, the count register is incremented by 1. And just like the previous case, when the count register value exceeds the preset register value, at that time the terminal count is reached and the output coil goes high. So this is the meaning. In some cases it may be a down counter, in which case the count register may be loaded with a preset register value and it may count down to 0 every time a pulse comes. So it may be an up counter, or it may be a down counter, or it may have up and down count inputs by which it can have. It can be also an up down counter. So excuse me, some basic a very simple example. You have a conveyor into which parts are supplied. So parts are coming from either this machine B, or parts of type B are coming, and parts of type A are coming. So you want to implement this logic that run conveyor when parts, X parts of A, at least X parts of A and Y parts of B are on the conveyor. At that time the conveyor will run. So this is what we want to program, and the arrival of a part of type B is asserted by this, and arrival of a part of type A is asserted by these two sensors. So what is the logic? So here is so this is an example of using counters. So you see that we have two counters. First of all, this is the master switch. The moment it goes on, this output is asserted. Now this now see that when IN001 is asserted, this IN001 also is asserted, and this IN001 is also asserted, and this IN001 is also asserted. So when this is 0, everything is 0. But when this goes 1, then all these rungs are enabled and both the timers are enabled. Now the arrival of part of type B is signified by this, and arrival of the part of type A is signified by this. So this is for A and this is for B. So every time a part arrives, there is a pulse here and the corresponding outputs are incremented. And now when, so the registers are incremented, not the outputs, the registers are incremented. So when the registers, when this register crosses, this output goes high. So it's in series. It's in series. So OP003. So when you put them in series, you want that both of them must reach their preset count values. Only then the conveyor will run. If you put them in parallel, it means that if any one of them reaches that preset value, then the conveyor will run. So this is an example where we can use a counter for an industrial problem. This is a nice example of counting how many parts per minute are going on the conveyor, let us say, which in a way indicates that what is the production rate. So it may be an important management information to display what is the production rate. So now therefore this is, so we want to count how many parts per minute. So we want to not only count parts, we want to also count it only over 1 minute of interval after we have pressed start for this operation. So obviously for creating this 1 minute interval we need a timer, and for counting the parts we need a counter. Therefore it's a mixed timer counter example. So here we have the timer and here we have the counter. Both have their, here it is loaded to 60 because we are talking about minutes and we are assuming that the internal clock pulses are available at every 1 second interval. So now suppose IN001 is a switch which one can press when he wants a measurement that over the next 1 minute how many parts pass. So when these two are, when this measurement desired contact is enabled, at that time both this timer and the counter are enabled. Now what happens? is that so when you say start, this is a kind of master switch. Then when you say start time, so you want to know of within this time of how many parts have passed. So you start time. So this goes high, and this goes high. Now this does not go high. So this is low. So now, and when this is on, this is also on. So now every time a part arrives, you get a pulse, so the counter goes up. In the meantime, after the time has expired, OP001 goes open, goes off. So this goes to 0, and then further parts are not counted. So this when this is going to 0, when this becomes open, whether this here you get a close or not, it does not matter. This cannot be 0 because these are in series. So therefore, at that time you in the counter you have the value. You have the value of how many parts have passed over the conveyor in the last minute. These are, so we have covered the timer and counter in some detail. Now we will take a very brief look at, there are arithmetic instructions, there may be logical instructions, specifically instructions like compare, instruction like doing ANDing, ORing. So all these instructions are available just like a low level language, and you can express them in various formats depending on the manufacturer, as I said. So in our format, we are saying that by this diagram we are saying that this, if you put this rung, it is a rung for doing the it will, when this rung will be executed, basically two operands, operand 1 and operand 2 will be added, and their sum will be put at the location sum, provided this enable logic is on. And this output coil may be used for various purposes. One of them could be that if there is an overflow, that has occurred during the summation, then it could go 1. So it can indicate an error condition and then be used in the further logic. So this is just an example of add. Similarly, you could have sub, you could have multiply, you could have various other things. This is just one example of an arithmetic instruction. Next is data move. So if you want to, again you depict it as a rung, because in the RLL everything is a rung. So in this case you have, again the data move will take place depending on whether the enabling logic is satisfied or not, and then data will move from source to destination, and maybe if there is some address failure or something, then, or maybe after the data has moved, actually this can become 1. So this can also be used for indicating condition after execution. You can have, so this is a data move. You can have various other functions, like you can have bit manipulation functions, you can have various kinds of block moves, etc. You also have various kinds of logical instructions. So apart from data transfer, the last instructions which are very important are program control instructions, by which we want to control. We don't want to execute all rungs of the RLL at all times, but rather we want to control whether we can skip some of them or enforce some of their values. So we have, typically, to give an example, we have a skipping facility, which, so when this is enabled, then this skip 001, this is a very special type of contact, so it is enabled. When it is enabled, then what it means is that the next n rungs, so you have skipped 001 and n is a parameter. So it means that the next n rungs will not be evaluated. They will when this is high. This is the meaning. So it's like, you know, it's like if skip not equal to 1, then, so this is like if skip not equal to 1, then this will be executed. If skip is equal to 1, as long as it stays 1, the next n rungs will not be evaluated and they will be maintained at the old value. Similarly, you can have another facility which we call the master control relay, which means that here, I mean, this is also a program control statement, and it means that whenever the enable logic is satisfied, then this MCR output coil, which is a very special output coil, is excited, and which means that the next n rungs will be set to their outputs. Each one of them has an output coil here, which I have not shown. So the next output coils, these output coil values will all set to 0. So without evaluating, irrespective of the logic in this branch, if this is excited, then they will be all set to 0. But if this is not excited, then they will be evaluated normal, like normal rungs according to normal PLC logic evaluation. There are some special instructions which also are there in a PLC RLL program language. For example, this is a sequencer. So a sequencer, this is actually the sequencer. This is the sequencer. So the sequencer is a block which can be separately programmed and which nicely executes a sequence of steps every time it is excited. So let us see what's happening here. So first of all, this is the master switch which will become on. Let us assume that and suppose this is off. So first of all, what happens is that this goes high. When this goes high and this is already low, so therefore there is a path from this place to this place, and even if this is taken off, this path maintains. Whenever there is a path here, immediately this is enabled and this is enabled. So when this is enabled, what happens is that when this is enabled and this is now reset. No, this is normally closed. Oh, this is normally closed. So when this is closed, it is already enabled because this is off. So therefore, and then this OP001 goes on. So when this OP001 goes on, it starts timing. So after a preset timing, this OP003 will go high. Now when this goes high, immediately what happens is that you get a pulse here. So in the sequencer every time it gets a pulse into its step input, it executes a particular set of outputs it will exercise. Okay. So a particular set of outputs which are bit outputs which are stored in some register. Okay. So there is a start register. So there are sequence of registers. Every time a pulse comes, a new set of register outputs. So you have register. Maybe these are three different or 8 different valves. So you have stored some values. So maybe even in the first step, this is 1, this is 1, this is 0, this is 0, and this is 1. That's the way you have programmed it. So when step 1 is executed, then these outputs will actually go to the feed. So the first pulse has come and the first step is executed. After the first step is executed, in the meantime, you see that so the first step is executed and it is waiting there. Now this has, when this has become 1, immediately this becomes 0 and it becomes 0 again. So again it's enabled. So now what happens is that and output 001 is already on. So therefore again it times. So basically what is happening is that it is with this arrangement it is continuously timing, and then the moment this OP003 goes high after the timing interval, this gives a pulse here. So a step is executed in the sequencer, and then because it's latched like this, so immediately when this goes high, this is again becoming reset, and then once it is becoming reset, it is, this one is enabled, and therefore it's again timing. So it's generating, continuously generating some timing intervals, and at the end of each interval you are getting a pulse which is executing the start register, executing the sequence register of the sequencer. At the end of the sequence has a fixed number of steps, so at the end of the sequence this will go high. So once this goes high, then what happens is that this one goes off. When this one goes off, then this one goes off, and when this one goes off, then there is no more timing here, and this itself, that is the sequencer itself, is disabled. So this is the way a sequencer works. Now, so this is what is expressed here. So if you press start button, IN001 is a start button, IN002 is actually a stop button. You could make the sequence stop at any times. So initially all output coils off, then IN001 pressed, then output 001 on and latched, then sequencer enabled, then timer starts timing, then at terminal time output 3 goes to high, and immediately sequencer steps and timer resets and immediately starts timing again. That is what we explained, and this cycle repeats. At the end of the sequence OP002 goes high, which means that the OP001 goes low and the sequencer resets and the timer stops timing. So this is how it works. So we have come to the end of the lesson, and in this lesson we have seen the various timers and counters, and we have also seen some arithmetic, data move and program control operations, and finally we had seen other macro operations like a sequencer. There are sometimes even some other continuous mode operations also like PID, etc., which we have not seen so far. So coming to the end, we have the usual points to ponder. For example, you could try to modify the die press controller such that a delay is introduced between, that is after the master control switch is put on and the up solenoid goes on, there is a delay. You can try to put that by modifying. Similarly, you could also modify the die press controller such that the number of die press cycles is actually counted. So you say that after every 1000 presses you want to stop the machine and you want to maintain the machine. So you want to count every time a complete cycle of die, there is one going up and one going down, is completed, and you want to count them, and after it reaches a count, you want to stop the machine for maintaining. Similarly, you could improve the RLL program, which we said in our earlier points to ponder, RLL program for control of a pump to keep the water level in a tank by introducing a hysteresis in your on-off control cycle. and and also sampling the water level every 30 minutes. That is not continuous sampling, sampling the water level every 30 minutes. So that is all for today. Thank you very much. In the next lecture, we'll continue with PLCs. So welcome to lesson 21 of the course Industrial Automation and Control. In this lesson, we are going to learn a structured design approach to sequence control. So far we have mainly seen the programming constructs, have seen small program segments, timers, counters. In this lesson, for the first time, we will see that given a practical problem, how to study the problem, what are the steps that you go through to finally arrive at an RLL program. So, and this will be followed using a very systematic approach, because as I have already told you that industrial control applications are very critical in the sense that if you have programming errors in them, they can be very expensive in terms of money, or in terms of even can cost human lives, etc. So it is always good to have a very systematic design process by which you can decompose a problem and then finally arrive at a solution. So we will look at the instruction objectives. The instruction objectives of this lesson are firstly to be able to model simple sequence control applications using state machines. State machine is actually a formal method, and we advocate the use of formal methods because English can be very ambiguous, sometimes contradictory also. So we have to model it using methods which are unambiguous, consistent, do not contain contradictions, and are also easy to understand and develop. Then from these formal models, we have to develop RLL programs for such applications. And for doing this, there are certain, apart from the RLL programs, there are some modern programming constructs which are being made available. One of them is the SFC, or the sequential function chart. So we'll take a look at that and also understand some of its advantages. So that is these are the instructional objectives of this lesson. So now let's go through the steps in basic broad steps in sequence control design. So first step is to study the system behavior. This is a very critical step, and most of the errors that happen in any programming exercise, not only this kind of industrial automation programming, any programming, mainly arises from the fact that the programmer or the developer did not understand the system well. So this is a very important step. So one need not really think too much about the logic. One should think about the logic while he is drawing the diagram. After that, the programming becomes automated. This is very useful. Okay. So now next, we'll have the output logic. Output logic is very simple, very simple, especially in this case. So the output logic says that if you are in state 2, then power light switch should be on, as we have given in our output table. So only thing is that look here, that we have also added some manual switch. You know, it can be sometimes we may need to check. We may need to do things manually also. So the power light switch will be on. Here we have put a manual switch. So if the PLC is running, then if we press the manual switch, then also power light switch may be made on. Similarly, we can have a manual down push button. So this is just to demonstrate that you can put additional logic to include manual operation of the system. So otherwise this program simply says that while you are in state 3, down solenoid will have to be activated. Very simple. Compare this with the kind of programs that we had written earlier. In fact, for this process itself, we had written some programs. So there, we did not have any concept of states and transitions. We were directly trying to write outputs in the form of inputs. Now the problem with this kind of problems is that here systems generally have memory. That is why you need the concept of states. It's not that if you get a certain kind of inputs, you will have to produce certain kinds of outputs. It depends on which state the system is in. So the concept of state is very important, and well, you can bring it down bring it possibly in certain cases using some temporary variables, but the kind of here you see if you look at this program says it's very complicated logic, and I'm not even 100% sure. It's very difficult to be 100% sure whether this logic is foolproof. It says that if the auto mode, by the way, this auto mode is actually a it's an auxiliary contact corresponding to some logical variable which you can set by a simple run, that if it is auto PB, and then you have an auto mode coil, and then you have this is auto PB, and here you can have auto mode. So you can have a auto mode coil, and this will be an auto mode auxiliary switch, so that the PB can be released. So this is a sort of a persistent input. So there is a single button in the garage and a single button remote control. So you can have either a button pressed in the garage, or you can have a button pressed from the remote, right? So there are two kinds of buttons. So you have either a button pressed from the garage or from the remote, then it will go to step 3 and it will start closing the door. This is the output. On the other hand, if button has been, so if from there, if either a button has been pressed either from local or from remote, or if we press a button, what will happen? Then the door will stop. On the other hand, if the limit switch is made, what will happen? The door will stop. So if either a button has been pressed or the bottom limit switch is reached, then immediately the door will stop. Or if the light beam is interrupted, then it will not only stop, it will actually reverse, right? So immediately it's going to reverse. Here what happens is that if you have pressed a button and to stop it, then if you press it again, then it will go to reverse. So this is you see, we have captured the behavior of the garage door in this form using SFC. So you can do a similar thing also for the traffic light. Let that be an exercise. So that brings us to the end of this lesson. Thank you very much, and see you again for the next lesson. Bye bye.